Blackbody radiation. We reach through the processes in the displays the Planck's spectral distribution of radiation from a black body at temperature T. The emitted radiation from a black body is represented by the thermal distribution of enclosed radiation in equilibrium with oscillators inside a cavity of temperature T. The radiation inside the cavity interacts with the enclosed oscillators. The oscillators have the Boltzmann's thermal distribution. Thermal equilibrium between the radiation and oscillators is reached when the radiation emission and absorption rates by the oscillators in the cavity are equal. The radiation causes the oscillators inside the cavity to absorb and re-emit radiation at rates proportional to the product of the radiation intensity times the number of the enclosed oscillators. Equilibrium of the radiation intensity inside the cavity is reached provided the proportionality constants for the induced emission and absorption rates are equal. Display 2 depicts two energy states atoms enclosed in a cavity of temperature T. The oscillators distribute between the ground energy 0 and an upper energy, epsilon. Boltzmann's distribution at temperature T gives the relative population of the energy levels. The emission and absorption of the radiation by the oscillators occur in the form of whole quanta, photons, of frequency nu, and energy h nu, with h being Planck's constant. In an induced emission process, existing photons of frequency nu inside the cavity force some upper state oscillators to de-excite to the ground state. The oscillators emit extra photons of the same frequency nu as the stimulating photons. Oscillators in the upper state may also spontaneously de-excite to the ground state without external radiation. The transition is viewed as a type of induced emission of radiation by virtual quanta of density ρ0, given in the display. The two types emission of photons are counteracted by induced absorption of photons by the oscillators. A corresponding number of oscillators in the ground energy level rises to the upper level. An equilibrium is reached when the emission and absorption rates of radiation are equal. Then the final number of photons becomes equal to the initial number. The detailed balance of the radiation emission and absorption rates in display 2 yields the Planck's blackbody radiation spectrum at temperature T, in display 3. The graph is a plot of the resulting Planck's blackbody radiation spectral distribution at temperature T. The spectral intensity peaks at h nu to kT ratio equals 3. Visit the website www.cyberphysics.academy for a full view of the tutorial. Send comments to contact@cyberphysics.academy.